Today we will be examining two pendula. Pendula A has mass MA and hangs from length of string LA, and pendula B has mass MB and hangs from length of string LB. The spring coupling the two pendula has spring constant denoted K. Notice that we have chosen our theta to be measured from the vertical position of each of the respective pendula, and the two masses to be equal to one another, denoted M, and the two lengths of the string to be equal to one another, denoted L. We then write out the kinetic energy of the entire system, where the first term corresponds to pendula A on the left, and the second term corresponds to pendula B on the right. We then write out the potential energy of the system, where the first term corresponds to the spring potential energy, and the second and third terms correspond to the gravitational potential energy on pendula A and pendula B. Notice that the potential energy is equal to 0 when the spring is unstretched, or in other words, theta A is equal to theta B, and when the pendulums are in the vertical position, when theta A is equal to theta B is equal to 0. We will write out the Lagrangian, which is just the kinetic energy plus the potential energy. Upon examining the Lagrangian, we see that there are two free parameters, theta A and theta B. Thus we expect two equations of motion, one for each free parameter. To find the theta A equation of motion, we will use the following formula: the partial derivative of the Lagrangian with respect to theta A minus the derivative with respect to time of the partial derivative of the Lagrangian with respect to theta dot A equal to 0, and use the corresponding equation for the theta B equation of motion. Written out, we see that they are very similar, but that they can be simplified by using a small angle approximation, or in other words, where the sine of theta is approximately equal to theta. Since we are dealing with harmonic oscillators, we will assume that it's possible to find values of omega such that theta of A is equal to A cosine omega t plus phi of A, and theta of B is equal to B cosine omega t plus phi of B, where A, B, phi of A, and phi of B are constants chosen based on initial conditions. Plugging theta A and theta B into our equations of motion, we get the following system of equations. Solving for omega, we see that there are only two possible values that will result in solutions to this system of equations. One value is omega squared equal to g over L, and the other value is omega squared equal to g over L plus 2k over m. Notice that I have used subscripts on the omegas to indicate the mode. I've done this because each mode results in a very different motion that we will be examining further. The first mode, or mode 1, is often called symmetric because pendulums have the same amplitude and the same phase. Or in other words, they act as a single pendulum. Mode 2 is often called antisymmetric because pendulums have opposite amplitude and opposite phase. In order to get a better understanding of these modes, we'll have to examine the motion of the system as given by the following equations for theta A and theta B. It's possible to think about them as a superposition of the two modes. First, looking at symmetric motion, we see that at time equal to 0, theta of A and theta of B both equal A, while theta dot A and theta dot B are both equal to 0. In other words, at time equal to 0, they both have the same amplitude, and they both have 0 initial velocity. We plug these initial conditions into our equations for the motion of a system and examine the initial position at time equal to 0 of the system. We see that A1 cosine phi 1 is equal to A, and A2 cosine phi 2 is equal to 0. We repeat for the initial velocity equations at time equal to 0, and we see that A1 is equal to A, and A2 is equal to 0, and phi 1 is equal to 0. Putting this all together, we see that for a symmetric system, phi of A is equal to A cosine omega 1t, and phi of B is equal to A cosine omega 1t. These are identical, and thus omega squared is equal to g over L, as it is for a single pendulum. Moving on to antisymmetric motion, at time equal to 0, we have initial conditions of theta of A equal to A and theta of B equal to negative A. However, theta dot A and theta dot B are both equal to 0. Another way to think about this is that they have opposite amplitudes initially and 0 initial velocity. These initial conditions alter our equations for the motion of the system, and thus we see that A1 cosine phi 1 is equal to 0 and A2 cosine phi 2 is equal to A. We do the same for the velocity equations of motion, and we see that A1 is equal to 0, A2 is equal to A, and phi 2 is equal to 0. Putting it all together, we can see that phi of A is equal to A cosine omega 2t, and phi of B is equal to negative A cosine omega 2t. and omega 2 squared is equal to g over L plus 2k over m. Visually, they start with opposite initial amplitudes and oscillate in opposite directions while stretching and compressing the spring between them. We're next going to talk about the very exciting and unique case of beats, which are neither symmetric nor antisymmetric, and have initial conditions that capital A1 and capital A2 are identical, and phi 1 and phi 2 are equal to 0. Thus, the equation of motion for the system become phi A and phi B listed here. The next step may seem rather strange, but what we're going to do is we're going to use an Euler's identity to transform our equations of motion for the system into what you see below, where theta A is equal to 2a cosine of omega 2 minus omega 1 over 2 times the cosine of omega 1 plus omega 2 over 2, and theta B is equal to 2a sine of omega 2 minus omega 1 over 2 times the sine of omega 1 plus omega 2 over 2. I've included a proof here, but in the interest of time, I won't be going through it. However, feel free to pause the video and take a look at it. The important thing that we gain from this transformation is that we can clearly identify omega B equal to omega 2 minus omega 1 over 2 and omega AV equal to omega 1 plus omega 2 over 2. Omega B is the beat frequency, and omega AV corresponds to the average frequency of omega 1 and omega 2. Since we have a good grasp on the theoretical aspects of a system of coupled pendula, let's look at how the system acts in VPython. Here we see two masses of equal mass hung from two strings of equal length with an unstretched spring connecting the two. As the initial conditions indicate, this system oscillates in a symmetrical manner, and thus will have an angular frequency of the square root of g over L, just as a normal pendulum does. Likewise, with different initial conditions, this system will oscillate in an antisymmetrical manner, with given angular frequency of the square root of g over L plus 2k over m. Note that in an ideal system, once a mode is achieved, the system will stay in that mode indefinitely. We will now look at a system that has been given the initial conditions that causes beats to form. The upper left graph is a plot of the amplitude as a function of time, and the lower left graph is plotting energy as a function of time of each of the pendula. Black lines are there only as a means to highlight the individual beats. There's a lot of very important things going on here, so I just wanted to highlight that a single period of the beats does encompass 2 full beats, and that any error between the calculated beat frequency and the experimental beat frequency is due to our original small angle approximations. The key characteristic of beats is that the energy alternates between masses, so that one pendula has all of the energy, both kinetic and potential, while the other has none, and then due to coupling, that energy is transferred. And with that, this concludes my video. Thank you very much for watching, and a special thank you to Dr. Amy Colon, my professor. However, if you're very interested in this topic, I've also designed and built several of these systems, so stick around if you're interested in watching a few demos. In all of these systems, we'll be examining synchronous, antisynchronous, and beats between these coupled pendula. In this first system, we see 2 pendula suspended by strings connected with a spring. This next system has no spring, but it is still a coupled system. This is because the masses are suspended from the same taut string. Another way to couple this system is to have both pendula firmly mounted onto a board that's freely allowed to move. This is done through the use of wheels on the bottom. And finally, we examine metronomes, which are simply force-dampened simple harmonic oscillators that are coupled by being on the same freely moving base. However, this is a very different system and does not form beats due to the forced nature of metronomes. In fact, these metronomes synchronize, but that's a story for a different video.